Okay, my friends, finally, what's going wrong in particle physics? This is why I lost faith in science. This is Sabine Hossenfelder, a very accomplished physicist. And she realizes nobody cares about the truth anymore. Okay, so let's start with Fermilab. This is Fermilab. This is Don Lincoln, neutrinos, Majorna, or Dirac. The neutrino is one of the most mysterious particles in the Standard Model. Well, let's see if we can figure out what it is. Okay, here's Fermilab again, all things neutrinos. Well, they say that neutrinos are strange particles. Scientists were quite surprised to find that the flavor of a neutrino changes as it travels. Now let's listen to what they have to say.
If we break the world down into the smallest possible parts, the smallest parts we can come to are elementary or fundamental particles, and there are 12 of them, and 3 of them are the neutrinos, and they come in 3 different flavors: the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are fantastically interesting particles, but difficult to study. They're electrically neutral, that's the neut part of them, and they're very tiny, that's the eno part of them. So neutrinos, electrically neutral and very tiny. So this is Argonaut, it's a neutrino detector. You never actually see a neutrino in the detector, you see the remnants of what happens when a neutrino hits something in the detector. Now the thing that complicates neutrino flavor is the fact that neutrinos oscillate between their different flavors. I can create a neutrino beam that's purely one kind of neutrino, and it can spontaneously morph into another flavor of a neutrino. Let's think of an analogy for neutrino oscillations, and we can think about one of my children's favorite topics, which is ice cream. So you start at the ice cream factory with your 3 standard flavors of ice cream: strawberry, vanilla, and chocolate, and you drive from the ice cream factory to the ice cream store, and what you don't anticipate is the time it took to drive the truck to get to the store. Some of the strawberry becomes chocolate. All of the strawberry and the vanilla become chocolate. That would be my children's preference. And that's what neutrino oscillations are. Your 3 flavors of neutrinos change. And so you measure them at the near site, what they started at the ice cream factory, and at the far site, what you actually deliver, and that tells you different properties of neutrinos. And that's the revolution in neutrino physics that happened just over a decade ago.
Well, I can agree with some of that, and I will show you that we can see those different transitions happening in our experiments. And again, that was Fermilab, because I'm going to keep responding to Fermilab. That's why I have lost faith in physics, is basically because of Fermilab. Okay, once again, Don Lincoln, Fermilab, and he's talking about what's the point. These are point particles and fixed particles. The black one's fixed, never changes. The red one here comes red and green, blue, and so forth, and that gets big and small and squishy. I have found these particles in our light experiments. They're using protons. I am using photons, which they wanted to use, never could figure out how to do it. We did it using a Venturi, which I will show you. Now, they refer to the Standard Model being the most successful of any particle physics there is, which is totally not successful. And then they also talk about the quantum foam, which I agree. The universe is filled with these particles of light. It says empty space isn't empty, obviously, because light is a particle, and those particles flow through space to get to where they're going to hit Earth to light it up. Okay, so here's Fermilab once again, the Standard Model, the most successful theory ever. Editor's note: physics in a nutshell is a new feature at Fermilab. Today in this column, Fermilab's Don Lincoln will define one commonly used term in physics. If you want a particular phrase defined or have a question, please contact Fermilab today, which I did. And I went back and forth with Don Lincoln quite a few times. And that's why I lost faith in physics, because of the intransigence. And you know, you try to figure out what you would term Don Lincoln's level of capability and how honest he is. Okay, so once again, Don Lincoln, don't forget, these are the smallest particles they've ever seen. They see this black one never changes as a fixed particle. This one gets big, gets small, and they say it has virtually no mass and no size, but it carries a field. So these are the two smallest particles they've ever seen. They see them together, they call them a Dirac neutrino. They see them apart, they call it a muon, and they call that an electron neutrino. When that electron neutrino hits heavy water, it creates a shower, and that's called an electron shower. All right, so let's see what we have here. This is Don Lincoln's particles. Once again, there's his particles. Well, there they are. We found them in our light experiments. Rodney Warren did these light experiments using a Venturi and pulsed lasers. Now, what happened at the Venturi? And what is a Venturi? A Venturi is a restriction. It's a funnel that forces anything coming into that funnel to restrict, just like a water hose. And it makes it accelerate, just like a water hose does. When you turn it tight, and it really takes off, and it's high-powered. Back here, it's just sort of dribbling out. Once it hits the Venturi, whoosh, and that forced the light to accelerate. Now, I thought Don Lincoln would see that, and I said, geez, Don, look at this. Look at what we did. We did it with light. We did it with photons. You guys are using huge particles. They're using big, big balls of particles like this, gigantic. We're using this. We're using that, one little particle like that, coming down and smashing through. Now, they can be green, they can be blue, they can be red. We've used all three different colors of lasers, and they all do exactly the same thing, and they all create the same particle. Only one is high-powered, the blue, the green is middle power, the red is low-powered. However, we did separate that muon neutrino, the black one, from the white one. Now, don't forget, here they are. The black ones and the white ones together, and this is a photon, that's light. You're going to see this very clearly in a second. These are the two particles that Don Lincoln would like to see, and they do see them in their colliders, but they see them literally in debris. As you can see, we see them face to face. We shake hands with those things. And you can see this one is not glowing a lot, and that one's glowing a lot, because that one's hitting all these little particles, which are in front of it. Now, whether you can see that or not, je ne sais pas. You can see those. And that's what's making that one glow. And that's what creates the oscillation that they talk about, which is the neutrino oscillation. And I'll show you that happening too. I have complete evidence to present. And I did. I presented it to Don Lincoln. And I was met with absolute rebuff, and not polite at all either. So he destroyed physics as far as I'm concerned for me. Okay, let's start with CERN. Everybody's heard of CERN. They have what they call the Large Hadron Collider, the LHC. Well, what it does is it sends particles, and I mean huge masses of particles, just flying through there, and one goes this way and one goes the other way, and then they smash head on, and then they get all kinds of trash and debris, and they sort through it, and they have found those tiniest particles. Look at this. The Large Hadron Collider, the world's largest, most powerful particle accelerator, started on September 2008, remains the latest addition to CERN. LHC's 27-kilometer-long ring of superconducting magnets in a circle, with a number of accelerating structures to boost the energy of the particles along the way. And now they just put in focusing, and they also put in CMOS detectors, so they could see instead of interfering with the particles. They're just picking up the radiation, which is the best way to do it. So they're coming along, but there's no reason to do this. And this is, over the course of time, I'm sure it's been trillions of dollars. Now, that's just CERN. Now, hold on a second. Listen to this. All right, now this is Fermilab Home, and they're the ones I refer to all the time. So here it comes. Boom. This is impressive. Look at that. My, my, my. We bring the world together. Do they bring the world together? Yeah, I'm not so sure about that. To solve the mysteries? I don't think they're really looking to solve much. And they have basically the same sort of thing. Basically the same sort of thing. Now, let's see what I can bring to the table in a little less money. Okay, this is CERN again, and what they wanted to do was what we are doing with photons. And they actually had a special meeting on this many years ago. Listen to this. This is CERN's own words. This is not me. The physics case for studying photon collisions, and that's what we use as light, as photons. The physics of photons collision has been a topic of some interest for many decades. Indeed, a special meeting in 1978, which is when I was deep into this, discussed the prospects of such collisions at the large, anyway, at LHC's predecessor. Now, these collisions are very clean as we're colliding photons, which is the elementary particles. They're elementary particles. They're the tiniest particles that exist. They are not composite ones like that. Like protons. That's what a proton is. It's 1823 of the particles I'm talking about. We're using one of the 1800, well, two of them actually. Anyway, this is the deputy spokesman for CERN. It was first proposed to do this type of physics as LHC many years ago, but the project didn't materialize then. Well, it should have, because it's been just denied by the people like Don Lincoln, literally. All right, just to back myself up a little bit, this goes back to, well, this is probably early 70s, but I was in the Army 1968. I worked on support for Nike Hercules missiles. I got very deep into all of this stuff, and I mean, deep. I had a lot of this stuff, and I went as deep as you can get into it. I did all the calculations, I did all the bond angles, I did all the dipole moments, and all of that stuff, and I found out nothing was right. What they were telling me just didn't work, and I kept showing it, and finally I just got away from these people because they couldn't take the truth. The transfer of energy is from light to atomic vapor. Atomic vapor is the dipole particles that I'm talking about, that I'm showing. All right, so let me try to explain what they did, make it very crystal clear. This is the type of fields that they see at CERN and Fermilab, and I can explain to you specifically why they see these patterns. They take two huge balls of particles coming this way, accelerate as fast as they can, bam, and they just explode. Well, the way these huge particles are constructed is the red is on the outside, and then by the time you get into the very center, which is the really tightly held stuff, you're into the blue. So the red just sort of bounces around and it all congeals around, and it gives you these kind of a field. These circular patterns, they call them Higgs fields. The other ones take off and they just never come back. So your Higgs fields are primarily the red that they see. We get Higgs fields in the greens. Well, let me show you what we get. All right, there's their Higgs fields. Here's our Higgs fields. This is the white electron shower, which that's what they're looking for, is that white electron shower. Well, there it is. And here's our monochrome particles. They're just red, basically. Now, we also can do them in green. And the green comes out identical to the red. Hold on, let me come up with some green. Okay, I just want to let you know, this goes back a long time between me and Don Lincoln, so I do sound a little bitter, and maybe I am a little bitter. And maybe you should be a little bitter. We're paying a ton of tax money, and we're getting nothing for it. And I believe we could almost get free energy now. if we just started to look at this interaction, which is this interaction, which is this interaction. And what it does is it creates enormous amounts of energy by forcing these particles to crush into their own fields. We did it a little different than Fermilab and CERN and all of them. Instead of having the particles hit head on, because they have fields around them, and they hit head on with the fields. Well, normally they'll drift off this way or that way. Very hard to hit them head on. We focused, and I actually went to the University of Geneva for particle physics back when I showed them this. I said, here's what we did. We separated these particles. They were impressed. I know they were, because they never said anything other than they watched what I told them, and I said, can we interact? And they said, no, we'll follow you on Facebook. And I said, okay. So I went under Coursera, and you can't talk to these professors anyway. They won't listen to you. All you can do is make your claims, and then they either tell you you're an idiot or they're silent. Basically, that's what happened to me. It was very disturbing. Anyway, they did end up just shutting CERN down and making their stuff focus just exactly like this, and using CMOS, which was they said you can't see that stuff because cameras can't see that. Oh, yes, they can. I said, we're using photons, and that's what cameras are designed to see. That's what they're there for. You guys are using protons. You guys are throwing hand grenades. That's why you're going to break your CMOS. We don't break the CMOS. The CMOS just kept running for years. I still have the same cell phone that we used, and they were cell phones. And they knew that this worked for picking up cosmic rays. Back in 2014, they were talking about using a worldwide network of cosmic ray detectors, which was nothing more than smartphones. So I am a little bitter, I suppose, if you want to take it that way, because this was like 2015, or I guess it was 2015. I had a video up that said light is literally contains dark matter and dark energy on its way to concussing with Earth. Hold on a second, I'll just prove that I did do that. Alright, here's how I've been posting about dark matter. This goes back 6 years ago. Light is dark energy until it hits matter and bounces. The research was virtually done at that point. Again, 6 years ago, light is liquid and it is dark energy. Light literally is a liquid. And then, of course, I was commenting on Sabine's latest one, where they don't even understand global warming. We're scrubbing through the particles that are in the universe. They just disregard them like they're not even there. Light is particles, and they are pushing and shoving against our particles that we're scrubbing against. And that goes back just 4 days ago. Here's 4 weeks ago. I'm showing my latest research on dark matter, light, gravity, anti-gravity. It's all very easy to understand now. A new look at dark matter. That was 5 months ago. Here's a year ago. It seems dark matter makes black holes and is half of light. It's just the hunt for dark matter and dark energy is over. I've been showing this quite a bit. And what have we got here? Well, I already talked about this, or I will. They wanted to do this back in 1978. They had a special meeting to think about how to use photons. Okay, here's my proof for the construction of atoms. They have a nuclear bomb that's going to explode. My contention is that everything is coated with the white particles because they push the dark particles to the center. That's why we've never seen them. Anytime you look at anything that has any mass whatsoever, all the dark particles are in the center. You never even know they're there. But if you dug inside, you would find that black matter. Now, when that explodes, all the white ones go first, then the black ones come afterwards. The white ones are burners. They don't push. They just burn. The black ones push and shove and don't burn. Watch this. Now, this is kind of slow. I got it on 25% speed. Now here, the first thing you're going to see just is a big, huge ball of light. Look at that. Nothing but light. Now what's going on? Just burning. No movement, just burning. That's the white particles. In a second, boom, here comes the black ones. Bam! That's it. Now watch. They will all come back because there's a void back there. They all have to come back to fill that void. All right, this is not very hard to understand. The white ones came first and burned, and the black one came right after it. That's the push and the shove. All right, let's get into the details. Don't forget Don Lincoln's particles, the smallest ones they can find. And we got them right here. And one glows, yes, he's correct, and gets bigger and smaller and has virtually no mass. Because in an atomic bomb blast, these burn the whole house down, and then these come from behind it and smash it, because these are just bowling balls. These are burners. They're like little flamethrowers, and these are just like bowling balls. All right, now that again is from Don Lincoln, and this is what we did, was took those particles, shot them down, accelerated them, and then separated the black from the white. All right, so that's the muon neutrino, the black one, which is these balls. And this is the electron neutrino, which is the white one that was attached as a dirac. And then they separated, which is what it does here. That's what they say. That's called Cherenkov radiation. And that happens when it hits like heavy water in a nuclear reactor. These really high energy particles, bam, they hit. And the black one just keeps going, and the white one turns into a shower like this. Now, instead of a new medium, we put it into a slit, which is so tiny and so restricted, and it's a funnel. The black particles keep slamming against the white ones, sorting them through there. That's what a Venturi is all about. It's a force of acceleration. Fully understood. Nothing, there's no mystery here. All right, so let's start from the beginning, the way light propagates. Normally you just see the room is sort of bright, and everything that bounces off the walls and so forth comes back at a certain color. But the same light is sent out all over the room. Same frequencies of light. But you see things in different colors. Why? It's because of the different things that it's impacting with have different bounce values. Let's go with that, bounce values. So red bounces back very easily because it's just on the surface of everything. Red is the weakest of the electrons being held on the surface of every other molecule. So if this was a molecule, the outside would be red, and you just barely bump it and you get red. It's actually, a lot of it is heat. But when you get way down inside, you're going to be where blue is, and pew, it comes out like a rocket ship. And that I can show you as well. So these are protons. That would be a proton. It have 1,823 individual little dirac neutrinos would make up one proton. So these are the tiniest particles, and they are the tiniest particles here, and they are the tiniest particles that I show in all these experiments. All right, now, what they did at CERN was they hit them head on and saw this just mess. And mostly the red, because it's on the outside of everything. When they hit hard enough, they get way down into the blue. That's when they get these really strong reactions, and they go, wow, look at that one. Well, they still have a bunch of red because you got to get past the red to get to the blue. Now, we are only using one particle. All right, so here's what happens on the pulsed red laser. Every single gas that's in the air has a bunch of particles. And every particle has one of those white particles. And if you bang into a white particle, it will glow. I don't care what happens. If I bang like that, I just made some of this stuff glow in a realm that you can't see. And you wouldn't just see that normally, but because of the dark way he did it. Rod Warren did these. They're absolutely fabulous. And so there's this absolute darkness, and the pulse, boom, 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 boom. And what's happening here? is the particle is right here. The wave surrounding it is a magnetic field. All right, so these magnetic fields of these particles have to interact. They glow. Anytime you push and these shove back, you get a glow. It's called the Casimir effect. Also very well understood. But they don't even understand what light is a particle. Don Lincoln, as far as I know, doesn't know whether light is a particle or a wave or what it is. It's just there. It's just something that's there. I have to ask him these questions if he refuses to answer. So this is light from a pulsed red laser. Each one of these is a pulse. It's just now beginning to accelerate because the Venturi is down here. Now let's look at that acceleration take effect. So don't forget, we got to push all these out of the way to make that wave go through in the first place. That's going to happen. But now it's starting to accelerate, and these are really going to start glowing. All right, so let's see the acceleration phase. Boom, there it is. Now, what's just happened here? That pulse red laser, boop, 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 all of a sudden we're seeing the particle come out of it. The particle is now visible. The only reason that particle is visible is because it has increased its push to shove. So it becomes visible as it pushes harder and harder and harder and harder and harder. Bam, 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 bam. And now it starts to glow. Now it's pushing back against its own self. Because this is banging, boom, it's pushing back, boom, 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 boom. So here's where your neutrinos are starting to form in here. I'll show you this. I can show you the neutrinos changing flavors as they go. Here is where the separation happens. The black separates from the white. Now the white shower is the only thing that's allowed through this tiny, tiny slit. Now, because it's all by itself, it says, I don't want to be by myself. I want one of you black guys to come back. And here's where they come back. As soon as they can get back together, they get back together. Now, this is a single slit. Why are we getting these exact stripes? Why are these little stripes coming out? That's pretty interesting. Well, the stripes are coming out because light is not like just a one straight beam. Light spins. And I can show you this and prove this as well. So when it spins, if it hits here, it goes over the top coming through. It sort of heads off this way. If it comes under the bottom and it'll head off this way. Most of them, there's going to be a whole flock of them coming through at the same time. So they're all over the place. So most of them are going to come through the center. But you're going to get some coming off that way. You're going to get some coming off this way. That is the way light travels. Can I prove it? Absolutely. All right, there it is right here. Light coming through is spinning this way. And there's a whole batch of them coming here. But the little slit is right here. So if it comes through that slit going this direction, we get it over here. If it comes through the slit going this direction, we get them on this side. So, but they all set up a pattern of these little stripes. And that's because as they come through, they say, get away from me, you get away from me, you get away from me, you get away from me. That's why you get these stripes. It's not because of a double slit and flapping over and this and that. It has nothing to do with that. That is because light spins as it goes forward. Okay, this is light speeding up. Light is not supposed to speed up. They claim that that's impossible. They say it goes the same speed in a vacuum, and it should slow down in the atmosphere. It shouldn't speed up. This is totally against any law that they can come up with. And this luminosity is off the charts. And this reverse EMF, this is what they call electromotive force, is off the charts. Just look at it way back here. That's because this is literally a nuclear, subnuclear explosion. That particle has divided. That's fission. This is fusion. This is the electron showers. These are the muons. They separated. We had them together. They separated. There is no question that that is what it is fission and fusion. 100% certainty. And that is what they wanted, muon neutrino and electron neutrino as a diarac to separate, which is exactly what we did. Now, we also can show that light can slow down. This is the blue, which comes through like a rocket ship. And you can't even tell there's two diaracs. But as it slows down, we can just barely see it. That they come, you can see the two diaracs together. It's the same particle. Blue is just too powerful to really see closely. Green we can see exactly identical to the red. Now that's a really up close and personal look at the green. And again, these are the two glowy particles, and they're just like two bar magnets. And what happens is as this goes through the air, forward. The glowing part will always be forward. All right, so this will come through. It'll start to glow like crazy because it's got to push the other fields. It'll charge up and then it'll go whoop, and then this one will come forward and it'll start to charge and that one will discharge. I can show you this, and I will in our experiment, showing the particles actually changing their neutrino values. And then that will charge up, and then it'll flip. And this one will charge up, and it'll flip. So that's what's going on. Flip, 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 flip as it goes forward. Now, can I show it? Yeah, absolutely. Okay, my good friends. So what are we looking at? This is one picture of, this is one shot of all of this happening at the same time, one particle going from pulse to pulse to pulse to pulse to pulse to explosion. So they're pulse red laser. Each one of these is a pulse. What happens is as they get closer and closer to the Venturi, they build more and more energy. If you look up here, there is no Venturi up here. And we're seeing virtually no increase in energy. There's still pulses. There's still pulses, but we're seeing no real energetic increase because they're not stacking up on each other, which is the neutrino flavors. This now is a neutrino. A neutrino, we see the white in the middle and two blacks, like an Oreo cookie. All right, and we don't see it up here because it's not directly in line with the Venturi. It has to be directly in line with the concussing particles that are in front of it. That's what happens. They're concussing with these that are pushing back. These aren't concussing with anything. They're just going forward. So they don't do anything. But back up here now, they're starting to concuss with this huge, remember I showed you that huge reverse EMF? They're beginning to concuss even up here, because of the concussion from the Venturi. I hope you understand this. So here they're at a certain value, they're pushing forward at 5 pounds per square inch. Then all of a sudden they feel like they're getting pushed back at. They're going to have to push more. So they end up at 7 pounds per square inch. It changes their structure a little bit. They go flat. And then they turn into white and black box here. And then it gets to 20 pounds per square inch because it's really getting pushed back hard. But it's got to go through there because the blacks, everything's pushing against it, one after another. Boom, boom, boom. It has to go through the Venturi. The black cannot fit. It keeps slamming the white separates, the blacks go around. Neutrino, I believe this is probably the tau, which is the heavy one, because white has no weight whatsoever to speak of. The black has all the weight. So you got two blacks and almost nothing in the middle. So its weight is almost all mass. This is 50-50, which is the photon. It has two whites and two blacks. So it's only got it's got a less of a density of matter, let's call it that way. And you see, these are started to stack up sideways instead of the Oreo cookie going this way. Now you got going up this way, and then you got them going like crazy looking stuff, and then they explode. That's what they're saying, all these different flavors, and they can't understand how that happens, and I do. It's because of the pushback. If there was nothing for them, they just keep going through. You see no neutrino flavors at all. They all stay the same way. See, there's the neutrino flavors of the green. There's the photons, the same photon we saw before, and back here, these were getting ready to change into photons. The green is very powerful compared to the red, and I can show that as well. All right, this is ultra cool. This is red, and this is green, going through the same slit at the same time, which is the venturi. And this is coming out of the venturi, the green obviously here, and the red here. This is actually the line that it would have followed if it was just going by itself. Now, they are interacting with each other's fields. And the green is extremely aggressive and much faster than the red. And when I say faster, the spin is much faster. Now, I'm going to come in and close into this because, as I showed you before, as they go forward, this charges up and that flips this way. That charges up, it flips this way. That charges up, and so forth. On and on and on and on until it stops. Now, it never, ever, ever, ever goes this way. Ever. Never. It's polarized towards the earth. It only flips in this direction here. Never goes this way, except here. And the reason is, the green is so powerful, it's doing its thing this way. Boom, 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 boom. And it's so powerful, it's spinning so many times, it's hitting the glowy one at the bottom and making it roll. I've never seen that before, ever. This is a rolling photon. I've never, ever seen that before. That is a one of a kind, my friends. That is a rolling photon. Rolling, rolling, rolling. Keeping photons rolling. Rawhide. Now, why do we have a black spot here and then all of a sudden they reconcuss out here? Well, that's a good question. Now, it has to do with the push to shove. It's coming into a new airspace at a high speed, and it's glowing its particles and making a division. Just like it does when we see it coming through and they separate, they push back and forth. It appears to me, I really can't explain this, to be perfectly honest with you. I'm sort of making things up right now. But I always do see separation zones between impact and in other words, this particle here is not this particle here. This particle has impacted other particles that are in here, and they now have turned into showers of their own. They call these electron showers. So that particle is now impacting with another particle here and starting it to create its own accelerated particle out there. That's all I can take from that. And that again needs some research, because you can see it trails down here. You see them all trailing down this way? I tell you, Rod did some fabulous work. I have exactly the same equipment he had, and I did some myself, but nothing like he could do. And he became so frustrated with the reception that I lost him. I can't get through to him anymore. I don't know. He sort of gave up on it, and I fully understand why. I kept saying, Rod, don't worry, we'll get this going. There's no question, we got this, and it never happened. And therefore, we are the ones that lose out. Because as I show you right there, if you could take, then they say luminosity. Luminosity is energy. The higher the luminosity, the higher the energy. We started with almost nothing here. We got luminosity on steroids. I say we can take that luminosity, which is nothing more than like extreme sunlight, basically, put it into a solar collector, which is a harvester right there, before it could get back to its black particles. These two pulling together is absolutely unbelievably, that is where you really get energy. And here we should get, they say, a minimum of 207 times. If you can separate the black from the white, which we did. No question, it's done. The black went away from the white is here. We could harvest right here, we should have 207 times the energetic value that started here. And because it's strictly photon energy, it goes right into electrons. That's what half of an electron is, the muon. The other half is the electron neutrino. That's what an electron is. This is the Dirac neutrino is an electron. It's exactly what my model is. This is a Dirac neutrino. The black and white together is the particles that I show right here. The black and the white together, black and the green, the black and the red, doesn't matter. Same particles CERN sees. And there they are as photons. Half of that, the black and the white together only, is an electron. That will stick to you. It wants to get attached to another one. When they're light in their energetic form, they're pretty comfortable together, and they have a magnetic field around them, which creates the wave, but it's driven by the particle. So that's the particle-wave duality. When we separate these, this is an electron. That's what burns stuff, an electron. If you separate the black from the white, that's when you get all of this extreme energy, which is right here. This is the muon neutrino, electron neutrino, the black and the white, and then the white turns into the showers. This is what they claim to be the holy grail of energy production for free. And we did it for almost nothing. And it can be duplicated very quickly, but again, stood in the way by Fermilab as far as I'm concerned. And I'm not backstabbing somebody here. I told Don Lincoln, I said, Don, this is very real. This is not I'm not a joke here. And you have to look at this. This is your job. And he said, we won't spend 1 minute looking at anything you have to present. And this was after I presented it all. And he came up with this, he said, oh, you can't see with a CMOS, nobody can see that. I said, absolutely you can. That's what CMOS was designed for, is to see these particles. And I sent him to articles that everybody was doing it. He had no clue about it. I said, we're seeing your particles. I'm seeing them interact. I understand them now. I sent literally all this stuff. And then what happened really, the real killer was this right here. Was the Russians. I sent Don Lincoln this. Okay, this was one of my first discussions with Don Lincoln, was about this black hole that the Russians found in space, injecting charged particles into a vacuum chamber in almost zero gravity. There's still some gravity. You can see that's sort of flattened out. If it was at the Earth, it'd be just one complete white line across here. All the particles would be pulled to Earth. Here, it creates an almost circular black hole. And I discussed this with the Russians as well as Don Lincoln. Well, Don just said, oh, dude, that's just nothing. That means nothing. But at any rate, this goes back to 2015. And this shows that the particles can be separated, which we did separate them. I showed we separated them. So it's not like they can't be separated. We know they're separated. And I said, I tried to convey this to Don, who I thought was interested in understanding these particles, and it appears that all he's interested in is, keeping the project going with huge amounts of money, when what we did, instead of billions and billions of dollars, was less than $1,000. All right, everything you see here, everything we did, was done with a Samsung Galaxy S3 smartphone. Goes way back. And using the selfie side. And Rod did virtually all this stuff. I didn't do any of these pictures whatsoever. Rod did. However, I did some experiments, but it was nothing like Rod did. Rod spent 5 years, 6 years, 7 years maybe. All he did was he originally put up some pictures on the internet. Just everybody thought he was crazy because they were just crazy looking blobs of light, but I could understand what I was seeing, and he worked with me for years, never got a penny out of it, never any recognition whatsoever other than what I've given to him, and he is the guy that deserves the recognition for making all this possible. All he did was he took a construction laser, which pulses to measure. It pulse, 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 and then it comes back and it tells you how far away you are. Well, we didn't care about that. All he wanted to do was take a laser. He just was playing around. And he took, instead of a flat plate with 2 slits, he took 2 finishing nails. That's all, just very, very, just little finishing nails, small nails. And he put them close together, very, very tight, and then focused this through it. And all of that stuff came out into the selfie. All right, this is what he did. That's it. That's it. That is the extent of the cost of what we did. Now, he used those other lasers too, the green and blue lasers, but they're, you know, they're the little tiny lasers. I mean, they're cheap stuff like this here. So I understand why Don would be upset, but that doesn't mean he's right to just dismiss it and keep just sucking the money out of our country to do all this crazy stuff. When we know already these particles exist, here they are. I see no reason to continue walking around in circles. Okay, this goes back to 2014. A muon, I showed you the muon, is the black ball. They say the black ball, it's actually the white one. It's the electron neutrino. Strikes a semiconductor, it underpins a smartphone camera, it liberates an electric charge through that CMOS. It creates a signature, and the pixels can be logged, stored, and analyzed. Cosmic rays emanate from beyond our solar system. Well, they're here on Earth too. We created them by what we just did. And they say you can turn your smartphone into a cosmic ray detector. This is back in 2014. I sent this to them. They, oh, no, you can't do this, you can't do that. Well, you can't with what they were using, these protons. But with photons, you can. So now they're, just right recently, this is in the last couple of years, they shut down to upgrade. Look at this. CMOS detector and system developments undergo major upgrade to increase the instantaneous luminosity. They focused and they're using the CMOS. Exactly what I mentioned when I went to the University of Geneva and to Don Lincoln as well. Okay, I've been very persistent at showing these things, the muon neutrino, which is the black ball, and the electron neutrino, which was the white one, or red or green or blue, whatever it is, and how that energetic particle forms showers. The muon is just a bowling ball, it just keeps going. Stays exactly the same, no change whatsoever. Now, this happens when Cherenkov radiation is from a muon produced by a muon neutrino event, yields a well-defined circular ring in the photomultiplier detector bank. Well, this one, the Cherenkov radiation from the electron shower, produces an electron neutrino event, produces multiple cones, and therefore is a diffuse ring in the detector array, precisely what I showed. And here I am showing it one more time. That's it. This is where it splits. The black splits from the white. You get the white showers and you get the black coming back. Now, if we could do what I am hoping we could do, is to harvest that right here. This is enormous amounts of energy. This is what they've been dying to see. And it's totally dismissed by the people we put our faith and trust in to work in our best interest. I don't think they're working in our best interest. That's not what I found. And I don't think that's what Sabine's found either. And that's what everybody that's commented on our page, her page, has also found. This is no interest in truth. There's interest in funding and keeping the projects running with as much funding as they can possibly get. Well, I've seen. Okay, she takes the exact same thing I'm taking out of physics. It's just not credible. Listen to what she says.
So what will happen to particle physicists? Well, if you extrapolate from their past behavior to the future, then the best prediction for what will happen is nothing. They'll continue doing the same thing they've been doing for the past 50 years. It'll continue to not work. Governments will realize that particle physics is eating up a lot of money for nothing in return. Funding will collapse. People will leave. The end. A lot of people are intimidated by physics. Don't be. It isn't magic, and if you didn't understand it at school, maybe the way they teach it in school wasn't the right approach for you. If you want to try a new approach to learning, have a look at the courses at Brilliant who have.
You know, that's funny because they contacted me to do some commercials for them. But anyway, she's right. But Brilliant needs to be looking from both sides of it too. That's what I proposed back to him. I said, I'd like to be part of this actual brilliance and, you know, be an alternative source of information. I don't care about getting any money for promoting anybody, and that's not my motivation. But we do need somebody to stand up. And right now, she's the best person I've seen. I'm impressed. I'm really impressed because she's going to take a lot of heat, guaranteed.